This is interprocess communication, again chapter 3. Okay, in chapter 3 we already discussed one thing called process scheduling. If you remember it, I mean the process concept, process has many states, new, running, waiting, ready, etc., etc. And process can be created, process can be terminated, and process scheduling, long-term scheduler, short-term scheduler, medium-term scheduler. So these are the first half of this chapter 3. That is first half. The second half here is inter-process communication. Okay, communication between the process, that you call inter-process, means between the process. Okay, that's the idea of inter-process communication. You know, in short, you can call it IPC, inter-process communication. Okay, operating system executes certain number of process, or sometimes it executes many process concurrently. It's also possible. Many different processes are executed concurrently. Remember the word concurrently, it's like at the same time, simultaneously. Okay, so sometimes let's assume 2 or 3 processes are concurrently executed. They are being executed, 2-3 process. Sometimes those 2-3 process may be an independent process. What do you mean by independent is, let's say you are executing one process, this is P1, and you have another process and then another process. Simultaneously, you are executing maybe 2-3 processes. You means operating system is executing 2-3 processes. Sometimes these 3 processes can be independent process. Independent means these are all different, not at all related to each other. Sometimes these 3 process may be a cooperating process. Cooperating process means like one process has to do something that has to be given to the another process, something like that. They are dependent on somehow. That is what you call cooperating process. Okay. So a process is independent if it can't affect or affected by other process. That is what you call independent. Independent means they don't share any data in between. They don't have anything in common, and the output of something may not be given to the other process. Or the execution of one process is not going to affect the another process. Something like that. They don't have anything in common. They're not sharing anything. You get the idea? That's what you call independent process. See, I mean to say it cannot be affected by other process, or it cannot affect the other process. Cannot affect the other process, or cannot affected by the other process. Okay, that means it doesn't share data. Okay, that is the meaning. They don't share data. They don't have anything in common. Okay, that's what you call independent process. Sometimes the concurrent processes may be independent. Sometimes maybe it can be a cooperating process. So mean to say, it can affect the other process, or it can be affected by the other process while in execution. Okay, that means that shares the data with other processes. I mean to say they have something in common. So they share the data, they share some resources. So that is something. Okay, so that's what you call cooperating process. So let's see the inter-process communication in depth. Okay, so let's see the cooperation. Independent process is fine. That's very simple type. But the cooperating process, I told you there is something in common. Like they share the data. Okay, so there are some reasons for providing an environment that allow process cooperation. So why do we need a cooperating process? What is that necessary? Let's see. They may share some information, or this is main reason for speeding up the computation. Okay, or maybe it's because of the modularity. We need a cooperating process, and maybe this is convenient. Having cooperating process is too convenient. So there are many reasons why to have cooperating process. Okay, first reason is information sharing. So let's assume that you have many users and interested in same piece of information. So there is a file. That file needs to be used by many processes. So we need to have an environment that allow the concurrent access to the that kind of information. You get the idea? Maybe you may have something in common. Maybe you have some files. That file needs to be accessed by all the 2-3 processes. So you need to provide such environment. You need to have some environment that allows this concurrent access to that file. This is one reason, information sharing. Another reason is speeding up the computation. Let's say if you want to do some task faster, so you do one thing, you break it into pieces, and then each pieces will be executed at the same time. At the end, you combine the output, combine the process. So something like that. You get my idea? So for example, simple example, I give you simple calculation. Let's say you have a square plus b square. This is one simple example. This is not a proper example. For understanding, I'm telling you. I want to do this computation. A square plus b square. If you want to do faster, okay, need to say one process will do a square. Another process will calculate the b square. The output may be given to the third process which will sum up them. Do you get the idea? So mean to say, so the two processes will be done concurrently, a square and the b square. So these two tasks will be done concurrently, and the output of these two processes will be added up to get the final answer. So in this way, you are saving time. Let's assume only one process is doing the task. The one process will calculate the a square, maybe it will take 1 millisecond, and it calculate the b square, maybe it take 1 millisecond, and add up the answer and it will take another 1 millisecond. So 3 milliseconds you needed. Instead, if you have concurrent processing, the time will be faster, shorter. Shorter means faster. Do you get the idea? This is for speeding up computation. Another one is modularity. You know modularity. Modularity, you studied it in Java. You know in Java, we have the breakdown of program. You have different classes. Each class has different methods. Each method is doing certain tasks. That's Java is main example for modularity. Good example for modularity. So you divide your program into sub programs. This is for the same reason it will be having faster process. Okay, that is one main thing. Okay, construct a system in modular fashion. So one module will do certain task, another module will do another task. So you are dividing the system functionality in separate modules. You can call it separate process or threads. You studied Java, it's called threads. Okay, each processing execution of each task is called thread. Okay, so that's maybe because of modularity we may have cooperating process. Okay, convenient. When you say convenient, so an individual user may work on many tasks at the same time. Okay, maybe the user may be editing or maybe listening to music or maybe compiling something in parallel. Parallel means at the same time. This is convenient for the user. If you say that you can do multiple tasks at the same time, of course it's very easy. If you say one task at a time, it will be time consuming. Okay, so the user can do many tasks. User can be editing, maybe doing some other task, another task, something like that. So that's mainly for convenience. So these are the reasons why we need to have cooperating task. Okay, so these are the reason to have cooperative task. Fine. And the models, the IPC models, cooperating, maybe inter-process communication model. The cooperating process require some kind of mechanism, IPC mechanism. Okay, so that it will allow them to execute or exchange the information between the processes. Okay, so cooperating process needs some certain type of mechanism to exchange the data. okay, or exchange the information. So there are two ways, or you can say that mechanism, two mechanism or two models, which are shared memory, message passing. Let's see the shared memory. When you say shared memory, now in your main memory, a particular portion of your main memory is going to be shared by the operating process. One particular memory, one piece of memory location is the one will have access to all the cooperative process. So the process can exchange the information by reading or by writing. So in the same shared location, they can read the data, they can write the data. Okay, that's the idea of shared memory. Another one is message passing. In message passing model, the communication takes place by means of messages. The messages will be executed. Okay, so you are going to have messages and exchange messages between the cooperating process. Okay, so that's the idea. Okay, can you see here the shared memory here in this diagram? You see the shared memory. So a portion of the memory is a shared memory. This memory is shared memory. So process A has access to this shared memory. Process B is also access to this shared memory. So this is one thing. Message passing. So this is the idea of message passing. So can you see here? Process A send a message and process B also send a message. So in this way, communicating processes can share the data or information. Okay, so in this way they can communicate with each other, exchange data. These are the two types of models we have. When you see the shared memory or the message passing, these two are the very common method or technique, IPC technique in many operating systems. Okay, some operating systems ask both of them. Some operating system choose to have one of them. Okay. So message passing is useful for exchanging smaller amount of data. You can't send a big message, okay? So because no conflict need to be arrived. So this is for smaller amount of data. Okay, message passing is easy to implement in distributed systems. So this is the advantage of message passing. Smaller data can easily be exchanged using message passing, and it's easy to implement. Okay, the another way, the other one, the shared memory, it's faster than message passing, because the messages are not going to travel from somewhere to somewhere. You just share the access, okay, access the shared memory location. Shared memory is faster because message passing system are typically implemented using system call. So you need to issue the system call execute, so it's time consuming. In shared memory, system call are required to establish the shared memory region. Only for the region, you just establish the region, set up one particular location in main memory, that is for shared memory. Systems calls are used to set up that shared memory location. That's it. After the memory is established, all the access is treated as a normal routine memory access. How do you normally access the memory? In the same way you are going to access that shared memory. That's it. So no system call, no kernel support needed. So faster. So this slide is talking about advantage of both the things. Here, first paragraph, we discuss the advantage of the message passing. In the second paragraph, we discuss the advantage of the shared memory. So you need to remember those things. Okay, fine. Okay, so let's continue with the shared memory. In case if the meeting got disconnected, we will continue back in the next class. Fine. Just only one thing I want to say for the shared memory, and then we will continue in the next class. Fine. Here, the shared memory, let's assume that you have the shared memory concept. Okay. This shared memory requires communicating process to establish the region. So first, the shared memory region has to be established. A shared memory region resides in the address space of the process, creating the shared memory segment. Like which memory creating the shared memory? So it's in the same process address space. So other process, whichever want to communicate using the shared memory segment, must attach to the address space. So remember this point. Okay. But remember, normally operating system try to prevent one process from accessing other process memory. So here in shared memory, it requires two or more process agree to remove this restriction. Remember, in operating system, one process can't able to access the other process memory location. There is a restriction. In terms of shared memory, this restriction is removed. So they can then exchange the data by reading, writing from the shared memory locations. So the form of data and the location are determined by the process, and they are not under the kernel's control, operating system's control. So the process find what data they are going to share and where is the data, address of the common data. Only the process is responsible for finding the data and where is it. Okay, not the kernel. Kernel means the operating system. It's not under the operating system. Okay. Do you get the idea? So the process are also responsible for ensuring that they are not writing to the same location simultaneously. Let's assume that if you are having a shared memory location, this is the memory location, and I have a process P1 and I have a process P2. So process P1 writes a data A equal to 5. So this is the data A equal 5. So process P1 try to write something for the value A. Process P2 also try to write something for value A. So process P1 wants to write A equals to 10. Process P2 can't say A equal to 80. No, you can't do that. So the process must make sure that they are not writing on the same location. At the same time, they cannot do that. They cannot write it. Can you get the idea? So the process are responsible for this. Fine. So how the process are responsible for this, how the shared memory locations will be accessed, we will see this one in next class. Is it fine? Good morning. So this class, we will continue the interprocess communication, chapter 3. Last class, we saw the reasons why we need to have the interprocess communication, something like why do the process has to cooperate. Okay, so these were the reasons we saw in the last class. There are 4 reasons for allowing a process to cooperate with each other. Cooperate means communicate with each other. Why do they communicate? The process, why do they communicate with other process? The reasons are, the first one, information sharing. So they share the information. That's what they communicate with each other. Or else computation speed up. So what you do, you have a big task, you divide the task into smaller tasks. So each process do the smaller task in parallelly. Okay. So in that case, after, in this case, after finishing all the process, task or over by all the process, when you combine them all, you have the final solution. In this way, you can speed up. Multiple processes are doing some task instead of one process doing the top to bottom. So it speeds up the processing. Modularity is constructing a system in a modular fashion, like part by part, something like dividing your system function into separate modules. Okay. This is what the previous point also, like one problem is divided into sub problems, something like that. So your one system is divided into many modules. And the last reason is convenience. It means Even an individual user may work on many tasks at the same time. Okay, like one user will be doing multiple tasks at the same time. So this was discussed in the last class. Reasons for the interprocess communication. For interprocess communication, we saw the reasons and we saw the modules, the technique for interprocess communication. There are two techniques, shared memory and message passing. So we saw these models in the last class. Shared memory means you have a region, shared region, a memory region. That will be here it is. So this shared memory region is accessible to process A and process B. Process A access this memory location, process B also. That's shared memory. One way of exchanging data and information. Another way is message passing. So it means to say that process A send a message and process B send a message, and using message passing exchange the messages between the cooperating process. We will see in detail the message passing after a while. So this is about the same. We already discussed this shared memory concept. Let's move on to the producer consumer problem. Just a second. So let's assume that if you want to know the concept of cooperating process, to say the processes are cooperating with each other, if you want to know more about it, just consider a producer consumer problem. Okay, a common paradigm for the cooperating process. So that is the producer consumer problem. For example, who is the producer? Producer is the one produces the information. And who is the consumer? Consumer is the one taking the information or using the information or consuming the information. So for example, compiler may produce assembly code. You remember the compiler? Compiler will translate your source program into object program. Of course, is it? So let's assume the two-way communication. You have compiler, you have assembler. So in Java, we have two-way compilation. So compiler takes your source program and produces the object program, assembly one, and that is consumed by assembler. What assembler does, it takes that assembly code and produces the object program, and that will be consumed by the loader. So producer is the one producing some data or information, and consumer is the one consuming that information. Okay, so if you want to understand the cooperating process, you just understand the consumer producer problem. Okay, so the producer consumer problem also provides useful metaphor for client server paradigm. You already studied object oriented programming, some of you are studying. In object oriented, even in network, you have the client server technique. So normally client is the one requesting something to the server gives something. Do you get the idea? That's the idea of client server. So the server is the producer and the client is the consumer. Okay, for example, let's consider the web server. The web server produces the HTML files, images maybe, whatever. And those are all consumed by client web browser. The browser that we are using, we are the client. Yahoo is the web server. For example, Google is the web server. So they produce the websites, or HTML file is the websites, or some images or whatever. That is the one producer. Okay, the web server, Yahoo web server or Google web server, or our college web server, whatever. Okay, and our browser, in your computer you have the Firefox, you have the Google Chrome. So that browser is the client. So this client is request some resource, like I want to open the college website. So producer is the one web server and I am the client. So I will be consuming the website. So I open the website here. Okay, I take it. Consuming means I take it, use it, something like that. Okay, so if you want to understand the concept of the cooperating process, just go through the producer consumer problem, which is a baseline for operating process or client server technique or whatever. Okay. So client server or whatever, producer consumer cooperating process. So here they use a common memory, a shared memory, so that they can share the information. Fine. So they use some shared memory to allow the producer and the consumer to run concurrently, because they need to run concurrently. We have we need to have some kind of buffer of items that can be filled by the producer and emptied by the consumer. Remember, you need to have a buffer. You must have a buffer. Okay, so that buffer means it's a small memory location. Don't confuse with buffer. Okay, so there should be a buffer available all the time. So the producer will put some information in the buffer and consumer will take the information from the buffer. Because I told you already, producer is the one producing the information, consumer is the one consuming the information. So let's assume that you have a small memory, we call it a buffer. So in the buffer, what is the idea? Producer fill this buffer with relevant data. And consumer takes this data. Okay, so consumer takes the data. So somebody is filling the buffer, somebody is emptying the buffer, taking the data from the buffer. Okay, so where is the buffer? This buffer resides inside the region of the memory. That's what we say before, shared memory. Okay, it's a small portion of memory, your main memory only, shared by the producer, also by the consumer process. So in your memory, you have a lot of memories, big memory. So in the big memory, one portion of your memory, a small location of your memory is your shared memory. Okay, we call it buffer, where producer fills the buffer with the data and consumer takes the buffer consumer takes the data from the buffer. Fine. This is about the producer consumer. How do they communicate? Okay. So they have a shared memory. Okay, this is the thing. Producer can produce one item, while the consumer consumes another item. Okay, so maybe producer is filling this part of the memory. Not necessarily consumer is taking. Maybe consumer is taking this part of the memory. Can you get the idea? So the producer and consumer must be synchronized. So the consumer doesn't try to consume an item that's not yet been produced. So they need to have some synchronized way of sharing the data. Okay. So if producer fills this area, then consumer can take it. If producer doesn't do anything, it's not yet produced. The information is not yet filled here. The consumer should not access this location because producer did not fill the data here. You get that? They need to synchronize, okay, the action, producer and the consumer. So two types of buffer can be used, not to be having a confusion. So how can they synchronize? So two types of buffer, we will be using it. The unbounded buffer places no practical limit on the size of the buffer. So unbounded means there is no limit for the buffer. Mean to say there is no range. Unbounded buffer. So what do you mean by no range? It's not like starting location and ending location. There is no such starting and ending location. Okay, that is what you call no limit on the size of the buffer. Okay, then that is what unbounded buffer. So the consumer may have to wait for new items, but the producer can always produce new items. Okay, so this is the case for the unbounded buffer. Consumer has to wait, but the producer always fill the new items. But when you go to the bounded buffer, there is a fixed size. So in your memory location, starting from this location until this location. This location address is 100, for example. This is the address. This address is 1000. So starting from this location until this location is the buffer size, fixed size. So in this case, consumer must wait if the buffer is empty. Okay, if the buffer is empty, he has to wait. So producer must wait the buffer is full. So if the buffer is full of data and consumer did not take it, the producer will wait until consumer takes some data. So for example, consumer emptied this location. So this location is empty. Now consumer can try to fill the buffer. Can you get the idea? So consumer will wait if the buffer is empty. Producer will wait if the buffer is full. You get the idea? This is the idea. But in the unbounded buffer, producer it's not going to wait. Okay, because it's unbounded, there is no limit for the shared memory. If this part is over, producer start to fill this part because this part is empty. If this is also over, producer fill this area of the memory. Producer start to fill the area, don't have to wait. Producer will not wait. Whenever there is a free location, he fill the location with the data. But consumer may have to wait for the new items. If there is no new items, he will wait for the new items. But the producer is not going to wait because he can fill anywhere in the main memory. That's the idea of producer-consumer problem. Is it clear? Producer-consumer problem. Are you all following? Yeah, okay, that's good. So let's continue. So this is the idea, but you don't have to remember the coding. Okay, so don't think that the coding is mentioned here and do I need to remember this? This is for explanation only about the bounded buffer. Okay, so how the bounded buffer works, that's the explanation in this slide. So when you talk about the bounded buffer using the shared memory, let's assume that you are going to use some variables reside in the region of the shared memory by the producer and consumer process. So they've got some kind of variables you are having. So the shared buffer is implemented as a circular array with two logical pointers. So it's going to be considered as a circular array. You know the queue, circular queue array is a circular array. So there is no end for the array. Okay, so it's a circular array. Okay, can you get the idea? So the variable in points to the next free position in the buffer. Out points. So here there are two. Here. There's two variables here. Just remember these two variables. So this is a circular array. What does it mean? There is no end at all. Okay. So let's see. So consider these two variables in and then out. Okay. So the in points to the next free location, next free position in the buffer. So you have a buffer, bounded buffer. Bounded buffer means it has a fixed size. So it starts from address 100 to address 1000, something like that. Something, just assume this way. So this in variable points to the next free position. So there are too many free positions. Just assume that. So in points, okay, for example, in points to this free location in the buffer. Out points to the first full position in the buffer. Okay, any position that is a first full position. Okay, let's say this is the full position. So it points to the first full position. Mean the location which is already full, something like that. So in case if the in value, if in and out are pointing to the same location, that means the buffer is empty. Okay, then so this is the idea. When the buffer is empty means in and out are going to be the same. Okay. Then if in case if let's assume that the buffer is full. What do you mean by buffer is full? Means in plus 1 divided by the buffer size, the remainder, if it is equal to out, that means the buffer is full. Okay, so let's see how does it work. So let's assume that. So this is the shared memory. Let's assume that this is the location and this is some other location, for example. Okay, in points to the variable, in points to the next free position, and out points to the first full position. Okay, first full position. In case if there is no value, okay, there is for the whole buffer is free. You don't have any data at all. So in this case, your in is going to be your in points to the next full locations, and also out points to the first full position. There is no first full position here. Okay, so both are here 0 and 0. Do you get the idea? So mean to say that there is no next full position, or there is okay, there is a first full position, there is no first full position, out is equivalent to 0. And your next full position, which is in is also is equal to 0. Both are equal to 0. That means the same. You can assume that the buffer is empty. Okay, so in this way, here why we need to consider this long thing is it? Because in the bounded buffer, consumer must wait if the buffer is empty, and the producer must wait buffer is full. So the consumer and the producer process, they need to know, is it the buffer full? Is it the buffer empty? So they need to wait. Do you get the idea? So how do they wait? They need to have some two variables. So these two variables will tell them, is the buffer full or is the buffer empty? Okay, so this is the small technique. And this is also another technique. So the buffer size, when you divide something, okay, let's assume that the full buffer is here. For example, the in is pointing to the next free location. So this 100, for example, this is the next free location, plus 1 divided by the buffer size. So when you divide this by the buffer size, if it equal to the out value, then you can assume that the buffer is going to be, buffer is currently full. So in this case, the producer has to wait because he can't write anything. There is no free space in the buffer. This is the way, but just understand that they have a technique and they use some variables to identify is it full or is it empty. Okay, we are not going to remember the code. We are not going to do anything. Even the formulas, it's not at all necessary. So just understand how do they, how the producer and consumer are going to understand that is the buffer full or is the buffer empty. That is the point. Is it okay? So here we are not going to consider this. This is the method. So saying that for the producer and consumer, okay, for producer. So here the producer will be checking, is it the buffer full? Then do nothing. Do you get the idea? So for the consumer, is it the buffer empty? Then you don't have to do anything. You get the idea. So in this way, consumer and the buffer are programmed to check the buffer, is it empty or not? So that they have to wait. So that's the thing. Okay, not necessary about the coding. This is not the not the necessary thing. We need to understand the concept. That's it. Okay. Now let's move on to the next thing. Before going to the next, let me tell you the same thing. In case if the meeting got disconnected, connect back using the same ID and password. Okay. Is it clear? Okay. Okay, let's see the bounded buffer. We are still in the bounded buffer. Bounded buffer means there is a fixed location, like 5 KB only or 2 KB only, something like that. So you have a fixed location, like let's say 5 KB or 2 KB, something like that. Okay. So in the bounded buffer problem, is to make sure that the producer, wait a minute. So the producer won't try to add anything if the buffer is full, and the consumer won't try to remove any data when the buffer is empty. But buffer is empty, so how can he take the data? And for producer, buffer is full, how can he write the data? Okay. So the solution for the producer is to either go to sleep or wait state until the buffer becomes not a location becomes free, until it gets a space to write data. Either the producer go to sleep or waiting state. Okay, and or else it can discard some data if the buffer is full. So it can take away some data. Okay. So the next time consumer removes an item from the buffer, it notify the producer. So buffer is now sleeping, for example, or buffer moved to the waiting state. Now when the consumer comes and it empty the buffer, it takes something from the buffer. So some location is empty. So it notified the producer, yeah, I took something already. So there is a free space, something like that. So it notified the producer. So producer starts to fill the buffer again. So in the same way, the consumer wants to take a data, but the buffer is still empty. So consumer can go to sleep or it can go to the waiting state. You get the idea? Because it doesn't find any data from the buffer. The same thing, when the producer writes a data, it notifies the client. Client means here the consumer. So this is the idea of bounded buffer problem. Okay, because it's a bounded buffer. You have a fixed size. That's the idea of bounded buffer. Okay, fine. Is it clear, everybody? Okay, I hope so. You all okay with this? Now let's move on to message passing, because there are two techniques. So that the cooperating process can share they can communicate. So IPC models, there are two IPC model, shared memory, message passing. IPC means inter-process communication. So there are two techniques for the IPC. One way to communicate is shared memory. That is the one we saw just now. There are two kind of buffer we are going to use in shared memory: bounded buffer, unbounded buffer. Okay. Now come back to the second technique, the IPC model. Second model is model technique, whatever you can say, message passing. Okay, so this is the second way of communicating, how the processes communicate each other. How? This is second way, message passing. So in case of the message passing, it gives a mechanism to allow the process to communicate and synchronize their action without sharing. So we are not sharing any memory. There is no shared memory at all. In memory, we don't have anything to share, but we allow the process to communicate. Okay. So let's assume that you have a distributed computing. So in case of distributed computing systems, this type of communication is very useful. Okay, where the communicating process may reside in different computer connected by the network. So this is the idea of message passing. Okay, then remember, message passing is used in distributed computing. Okay, then why? Because in distributed computing, the processes are not going to reside in one computer system. Maybe one process in one computer system, another process in another computer system. Okay, because they are connected in the network, distributed environment. You get the idea? So, for example, in internet chat program, just this is a very simple thing, internet chat. It could be designed so that chat participants communicate with one another by exchanging messages. Now we are chatting here in the class, is it? I'm at home here, you are somewhere. Even though you say that it's like a kind of Jubail, but different locations. Moreover, different kind of machines we are using. You get the idea? It's not the same machine. So we are connected by the networking and we communicate. So we are considered as each process. So we exchange the messages. Okay, fine. Okay then. So this message passing facility, we have two operations, of course. What are the two operations? For example, I send a message, so I'm sending, and you receive the message. Send and receive, and you send and I receive. You get the idea? So this is the two operations in the message passing, sending, receiving. So the parameter is message. I send a message and you receive the message. Okay, then message are sent by our process that can be either fixed or variable in size. Okay, so it can be sent by a process. So the process may be a fixed process, fixed size process, or variable sized process. If only fixed size messages can be sent, so in this case, system level implementation is straightforward. Example, having a fixed size message, then that's fine. But in case if the messages are going to be a variable sized message, so we need a kind of a little different implementation. Okay, so that's the thing. So the message is shared between the two processes. Is it going to be a fixed size message or a variable size message? If it is a fixed size message, then system level implementation it's very easy, straightforward. Okay, so let's see those things. Because for fixed size system level implementation is too straightforward, means very easy to implement. But for variable sized message, system implementation is going to be little complex. Okay, so it's not, I can't say little complex, it's more than little. Okay. So this is the main trade-off seen throughout the operating system design. So let's see let's see one example. Let's assume that we have two processes. One is P and one is Q. So there are two processes. Okay, one process is called P and another process is called Q. So they want to communicate. So let's assume that they must send messages. They receive messages. So we are in message passing. P and Q are communicating by sending messages. Okay. P sends a message maybe, or Q sends a message, or whatever is it. Let's see example. So there should be a communication link between these two processes. Okay, there should be a link. Link means a path. There should be a path that should exist between the process P and Q. If you have a link, a path, P can send the data or Q can send the data. Okay, just a second. So there should be a link or a communication link or a path should exist between the two. You get my point? So the message passes through the path, the communication link. The message is traveling on the link. Okay. The link can be implemented in variety of ways. So what are the ways the link can be implemented is, we can have a physical. Okay. We were discussing about the two process. If process P and Q wants to communicate, we need to have a link, communication link between them. So how are we going to have this communication link? The link can be implemented in many ways. So here we are not going to bother about the physical implementation. Okay, but we are going to concentrate on the logical implementation of the link. Okay, so there are many methods for logically implementing the link and the send and receive operation. So how the logical link can be implemented and how the send and the receive operations are going to be done. So we have here direct, indirect communication, synchronous, asynchronous way of communication, automatic, explicit. Automatic means implicit. Implicit, explicit, buffering. So there are many methods we have. We will discuss one by one. Let's see the direct. First one is direct, indirect communication. Is it? Direct means very simple. From the name you can say that. Like P send the message to the Q, is it? It's directly sent to the P. P, for example, maybe Q send the message, so it directly sent to P. And P sends means P send it to Q straight away. It's too direct. Okay. From the name you can say that each process which wants to communicate must explicitly name the recipient and the sender of the communication. Okay, so for example, sending, Q is send, for example, Q is sending a message. So here the meaning is send P comma message. So it goes to P and this is the message. And receive, for example. So this is the person who is sending the message and this is the message. So Q sends the message and this is the message. So receive a message from Q. Okay, something like that. So straight away you mention the message, to whom it is going and from where it is coming. Okay, from where it comes or else to whom it is going. You get the idea? This is direct communication. So let's concentrate on the link between the P and Q, means sender and the receiver. The link is established automatically. Okay. Every pair of process that wants to communicate, let's say P and Q wants to communicate, automatically the communication link is established. Process needs to know only each other's identity. That's it. P has to know the ID of Q. Q has to know the ID of P. That's it. Okay. So the link is associated with exactly two processes. So let's say this is one process. This is another process. So it can connect only two processes. You get the idea? So it is connecting only two processes. Okay. Exactly two processes only. So between each pair of the process, so you can have only one link between a pair of process. Okay, you can't have more than one link between a pair of process. Okay, there is exactly one link between pair of the process. Okay, this is about direct communication. And let's concentrate some more. Let's see. Okay, so here this direct communication, it shows the symmetry in addressing. Okay, that is both the sender process and the receiver process must name the other, communicate. Let's say I was telling here, Q is sending a message. To whom it is sending? To P it is sending. For example, here, for example, this is P is receiving a message. From where it is receiving? From this. Maybe this is Q, for example. So both the sender and the receiver has to name the other person in the communication. So in the method call, you need to name the other process. Okay. Only the sender names, sorry, for example here, only the sender names the recipient and the recipient name the sender. Okay. Here, recipient, it's receive ID comma P. So okay, for example, you need to understand one thing here. Here one thing is sending this message. Okay, so I'm sending this message to the process P. Send a message to the process P. So here when you have the receive, you can receive from P for Q or for S or any other process. So from any process. Okay then. So the variable ID is set to the name of the process with which the communication has taken place. Okay, so you can change the ID by P or Q or whatever, the name of the process. So you can write the name of the process. Okay, this is about the direct communication. You have, remember the points, the key points in direct communication. The key point is there is a link established automatically. Remember this point, automatically the link is established between the two processes. So there is exactly one link between the two processes. You cannot have many link between the two. Okay, and the link is only between the two processes. So remember this, the link is between the two processes, and between the two processes there is exactly one link. Remember these points in direct communication. And for indirect communication, it's indirect. Indirect means you don't know to whom it's, you are not mentioning that this message is going to P. You know, in the send operation and in the receive operation, I'm not going to mention to whom it is going, and I'm not going to mention from where it is coming. So, but how do I mention is, I will be mentioning something else, like the mailbox name. Here, A is the mailbox name. So I'm sending the message to the mailbox. I'm receiving a message from a mailbox. So here we will be using a mailbox. Okay. You can call it mailbox or a port. Okay. So it can be viewed abstractly as an object into which messages are going to be placed by the process, and from where messages will be removed by the processes. So each mailbox has a unique identification. The name is going to be different. Okay. For example, a process can communicate with other process via a number of mailboxes. Okay, so it can communicate with any other process through the mailboxes. Okay, so let's assume that P and Q wants to, let's say P, this message or this process wants to share a message to Q. So how do they, using indirect method, I told you, they're going to send and receive message to the mailbox, is it? I may have maybe multiple mailbox. I may have mailbox A, mailbox B, mailbox C. Do you get the idea? So I have many different mailboxes. So how P is going to send a message and how Q is going to take a message? Is it in mailbox A or mailbox B or mailbox C? So confusion, is it? Remember, this P and Q can share the messages through mailbox, which is shared mailbox. Remember, there should be a shared mailbox between the process, and through the shared mailbox only P and Q can communicate. So process can communicate only through the shared mailbox. Okay, so this is a shared mailbox. So P sent a data and Q moves the data. Okay then. So just mention the mailbox name in the send and receive operation. Remember, to a shared mailbox. So the link, again, you need to concentrate about the link. So the link is established between pair of process only if both the members have a shared mailbox. In case there is a shared mailbox, then only the link is established. If there is no shared mailbox, no link is established. Okay. So the link can be associated with more than one process. So you don't think that I will be having only exactly one link between the two processes. No, the link may be associated with more than two processes, just opposite of the previous. Okay. Between the pair of the process, number of links may exist. Don't think that only one link exists between the two processes. Pair means two processes. Okay, there may be multiple links. So this is just opposite of the previous case. Okay, remember the points. Okay, and talk about the mailbox. The mailbox may be owned by process, or maybe it can be owned by the OS. So don't think that the mailbox is owned by the process only. Sometimes mailboxes may be owned by the operating system. So if the mailbox is, just a second. If the mailbox is owned by a process, then we distinguish between the owner and the user. Owner means who is the owner of the mailbox. Okay, so the owner can receive the messages and the user only send the messages. Remember this point. Okay, I have a owner means I'm going to, in the post office schemes, if you remember the post office, back home in my country, we have some kind of posting service. Here, I don't know. They distribute the letters to the homes. They come to home and they distribute the letter. So at the gate, in the entrance, we put a mailbox. So the postman will come and he put the mail inside the box. So that mailbox, he just put the messages. Let's say I want to send a mail to somebody. I'm not going to put it in the mailbox. This mailbox only for receiving. So if I want to put it, I need to go to the post office or somewhere. Can you get the idea? In this way. So remember, owner of the mailbox can only receive the mails, messages, and the user of the mailbox can only send the mails, messages. Okay. So this is the idea. You have to remember the indirect and direct, the difference on also. Okay. How about the communication link? So you need to know the differences. So communication in client server. I'm going to give a small introduction only here for client server. We are not going to go in depth. Okay. So because some of you, if you follow the old degree plan, you are studying or you might have studied the object-oriented programming. In that object-oriented programming, we have the client-server system. Okay, we saw the sockets, we saw the port, and we send message, receive message, something. So we already had these codes. For those who are following the new degree plan, maybe in the networking, you may study something, but not in Java programming. Okay. So I'm just going to give an idea only, not in depth. So let's see the communication in the client server systems. Okay. So until now we were talking about message passing. So how process can communicate using the shared memory or using memory message passing. So these are the things we discussed. These techniques can be used for communication in client-server system. In networking, we have a server and many clients are connected to the server, and clients need some, clients can share the whatever files or application or whatever resources from the server. That's it. So the same technique, shared memory or like message passing, can be used in the client server system also. Okay, so there are some strategies for communication used in client server system is socket and RPC, like remote procedure call. Okay, so let's see. This is the technique used in client server system. This is also for communication. Socket and remote procedure call. Socket is the endpoint of the communication. A pair of the process communicating over the network has a pair of socket. Okay, let's assume that this is process P and there is another process wants to communicate. Let's say this is Q. So there will be a pair of socket. So this is endpoint of the communication. So process P and Q going to communicate through this socket. So this is the socket, maybe server socket and client socket, point of communication. So the socket is identified by the IP address connected to the port number. Okay, so this has an IP address and the port number, and here this socket also has IP address and the port number. Okay. In general, socket use a client server architecture. So the server waits for the incoming client request by listening to the specified port. Once the request is received from the client, server accepts the client and makes a connection. Okay, so this is the idea of, so let's assume that this is a server